Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwar, your physics faculty. Today we are about to deal with session number 56, first year Neet. The chapter name is Laws of Motion. In the previous session we have discussed about second law of motion and its applications. Okay, we have particularly under one heading, applications of variable mass. We have seen different cases. We have solved one or two problems connected with yesterday's discussion. Okay, so in today's session, we'll continue with two more important concepts. One is impulse, the other one is conservation of linear momentum. Let us see what we can do. Okay, so let me start with impulse. Before I start with impulse, we'll try to understand few of our practical experiences. You guys might have seen a cricket fielder, trying to catch the ball. How he catches the ball? When the ball is reaching his hands, he won't keep his hands like this. He won't catch the ball directly like this. While catching, he does something like this. What? He catches, he catches the ball with this kind of motion, with this kind of movement of hands. Why he does like that? What happens if he catches directly like this? Yeah, I think some of you know that if he catches the ball directly, it hurts our hands. Whatever force that the ball is supposed to exert on our hands, it will be exerted on our hands in a very short interval of time. In a fraction of seconds of time, the entire force acts on our hands and it hurts. But when you do it like this, while catching the ball, what happens? You are actually slowing down the ball. You are decreasing the velocity of the ball. The time for which the force that ball can exert, the time for which the force can be exerted by the ball, that time you are increasing. Earlier, when you are catching the ball like this, in a very short interval of time, in a fraction of seconds, what is happening? The entire force connected with the ball is transferred to our hands, isn't it? And it hurts. But when you do it like this, whatever force the ball can exert on your hands, that acts continuously over a time interval, isn't it? So slowly the force that ball can exert on our hands, is taken over a interval of time. Okay. So because of this, you don't get hurt when you are catching the ball. So this is a very practical experience to all of us. Not only you have seen automobile, bike, or any kind of automobile, car or bus or lorry, whatever it is, whatever vehicle it is. All these vehicles are fitted with springs kind of arrangement. Okay, springs kind of. Actually, for large sized automobiles, the structure of this kind of arrangement will be different. But if you imagine a bike, to the back wheel, two springs kind of arrangement will be there. Okay, if at all, if those springs are not provided, what happens? What happens? Whenever the vehicle travels on the uneven surface, there will be a lot of jerky motion, and we don't feel that much comfort when we travel on uneven surfaces if springs are not provided. Even for bicycle seat also, springs will be there. Okay, for some bicycles, for few bicycles, not for all bicycles. Those springs are meant for what? Decreasing the impact of a force when the vehicle is traveling on uneven surface. Okay, so like the way a cricket player, a fielder particularly, when he is trying to catch the ball, he pulls his hands in the backward direction so that the impact of a force can be decreased. The impact of force can be decreased, or the impact of a force can be extended over a long time. So that's how its influence decreases. Okay. So these things are something they are connected with time for which the force acts. In case of cricket player, if he catches directly, in a short interval of time, the entire force acts on his hands. When he pulls his hands like this while catching the ball, the time for which the force acts on the ball, on the hands increases. Because of that, we don't get hurt. So the time for which this force is acting is something that you can consider as a significant physical quantity to be studied in physics. It's a very important physical quantity to be studied. And that's what named as impulse. whatever kind of examples I have discussed with just now, all these examples fall under the category of impulse. Okay, so what is impulse? Basically, impulse gives us an idea about how much impact the force is creating. How much impact the force is creating. You can write like this. Impulse measures impact of force. Measures impact of force. Mathematically, it is expressed like this. It is denoted with G. J is equal to product of average force acting and time for which it acts. Impulse is a vector quantity and its direction will be along the direction of the force. So how does it is expressed mathematically? Impulse is expressed as a product between the average force that is acting and the time for which it is acting. So FAVG into T. Okay. So let us try to have more discussion connected with this one. We have already seen the Newton's second law of motion. According to Newton's second law, what you can write? F can be written as, or F bar is equal to dP bar by dt. dP bar by dt. That's how it can be written. Okay. Let me shuffle this one. How it can be written? F bar dt is equal to dP bar, integrating on both sides. What you can write? Integral F bar dt is equal to integral dP or integral dP bar. Let us say the time has changed from t1 to t2. So corresponding to t1, let the momentum is p1. Corresponding to t2, let the momentum is p2. Okay. If it is further expanded, what you can write? This one, integral t1 to t2 f bar dt is equal to, this can be expressed as integral dp bar is p bar, like integral dx is x. Okay, so p bar, apply the limits p1, p2. This can be further written as p2 bar minus p1 bar, or it can be written as simply change in momentum. Final momentum minus initial momentum is nothing but change in momentum. And corresponding LHS part is what? Integral T1 to T2 F bar dt. Whatever force we are dealing with, if it is a constant force, whatever average force is there, if it is constant, I'll take it out, and then how it can be written? Integral T1 to T2 dt is equal to delta P bar, isn't it? And further, integral dt is what? T. So if limits are substituted, finally we'll have T2 minus T1 is equal to delta P bar. Something like this. Average force multiplied with total time taken for the action of force is equal to what? Change in momentum. But actually this is what? This is equal to impulse. So impulse is equal to average force multiplied with time for which the force is acting, and here force multiplied with time for which the force is acting. T2 minus T1 is what? Time for which the force has acted on the body is equal to change in momentum. So this is nothing but impulse. So impulse can also be written as a change in momentum, isn't it? From these two equations, that's what you can write. Let me take this as equation number 1. Let me take this as equation number 2. From equations 1 and 2, what you can write? From 1 and 2, what you can write is impulse is equal to change in momentum. Change in momentum. And this change in momentum is equal to F bar into T2 minus T1. Or simply you can replace this with a T. If at all T2 minus T1 is equal to T, what you can write? F bar into T. Okay. So this is a very important conclusion. Provided here what we have done, this f bar, if it is constant, then only you can bring it out of the integration. If it is time dependent, you cannot bring it out of the integration. Time dependent in the sense if force is variable. So if you are dealing with a problem where f is a variable, if f bar is a variable force, then the impulse is expressed as, impulse is basically what? Change in momentum. Change in momentum in case of time varying force is what? This one, integral t1 to t2 f bar dt. So whatever force you are dealing with in case of impulse, if that force is time dependent, if that force is a variable force, then you have to make use of this equation to deal with calculation of impulse. Okay, if at all whatever force he is talking about in the question, if it is constant, then you can make use of this equation to find out impulse. And in nutshell, what this impulse is, impulse gives us measure of the impact of a force. When a force is acting, how much impact it can create. Okay, so that's what it gives us. Okay, so let us try to understand few other points connected with this one. Okay, I'll consider one FT graph. Okay, FT graph. Before that, I want you to remember these facts. Impulse is a vector quantity, and if you want, you can express its units also. Units, how the units can be expressed? Units of force, it's newtons. Units of time, it's seconds. So let me write that data also. This is a very fundamental data, and of course, sometimes when you face conceptual questions, it helps us to understand, those questions, and we can answer. Okay, here J bar is a vector quantity, and its units can be written as Newton meter, SI units, and what else we can talk about? The direction of J bar. The direction of J bar is along the direction of force. Along the direction of force. The other thing is dimensional formula. If you want, you can write the dimensional formula. Dimensional formula. How it can be written? Dimensional formula for impulse. It is product of force and time, right? Force dimensional formula is m power 1, L power 1, T power minus 2, and times dimensional formula is T. So dimensional formula of impulse can be written as m power 1, L power 1, T power minus 1. That's how it can be written. Okay, so these are fundamentals connected with this one. Okay, so let us try to understand the FT graph. So let us say average force data is available with us, and the time for which it is acting, it is also available with us. And if we make a plot between F average and time, okay, so what kind of details we can extract from that, we'll see. Okay. FT graph. Let us say average force is taken on the y-axis and time is taken on the x-axis. Let us say we are dealing with a system where average force is constant, it is not changing with the time. Okay, if this is the situation, let us try to understand the area enclosed by this graph, area enclosed between the graph and this time axis. How it can be written? Let us say here F is the value of average force corresponding to this point, which is a constant with the time. Time is increasing, but that F is not changing. Corresponding to this final point, time, I'll take it as T. Therefore, area under the graph is equal to what? F into T. Is that right? This is the F, this is T, like length into breadth. F into T. But average force multiplied with the time for which it is acting is what? It is nothing but change in momentum. Change in momentum, here it is nothing but impulse. Well, we're getting area, no? Just we'll get the magnitude. So this magnitude of Ft is nothing but magnitude of change in momentum. That magnitude of change in momentum is nothing but magnitude of impulse. So here, one important physical significance you can identify from this Ft graph. When you calculate area under the Ft graph, it gives us impulse. It gives us change in momentum. If there are any questions, numerical problems connected with the Ft graph, and if there is a question connected with the change in momentum, if there is a question connected with the impulse, you can calculate by just finding the area under the graph. Because we see it clearly here, area under the graph gives us what? Impulse or change in momentum. This is one very important physical significance. And one more point. For example, there are two sets of details, like one average force is F1, corresponding time is, let us say, T1. Another average force is F2 and corresponding time is T2. So this T2 is what? Time for which this average force is acting, and this T1 is time for which this average force F1 is acting. There is a possibility like, F1 into T1 can be equal to F2 into T2. How is that possible? For example, in this case, let us say F1 is less than F2. What if T1 is greater than T2? Yes, then product of F1 and T1 can be equal to F2 into T2. Is that right? It means for the same impulse, for the same change in momentum, two sets of forces and times are possible. Okay. If the force is less and if it is acting for a long time, okay, corresponding change in momentum can be equal to large force acting over a short interval of time. Okay. So if you wanted to increase the impulse, if you wanted to have more change in momentum, what you can do is either you can increase the force or you can increase the time for which it is acting. In either way, you can actually tune impulse or change in momentum. Okay. So these are a few fundamental details connected with impulse, and whatever examples I have quoted, a cricket player catching the ball, he prefers to pull his hands in the backward direction so that time for which the impulsive force acts on his hands can be increased and the impact can be reduced. Okay, shock absorbers provided, whatever springs I was talking about in case of automobiles, like in case of a bike, that is called as shock absorber or shockers. Simply you can call it as shockers. Why do automobile manufacturer will provide those shock absorbers to the vehicle? To increase the time of impact of force. That's the reason. When your vehicle, if it is traveling on a road and if there is a pit on the road, if vehicle tire goes into the pit, what happens if shock absorber is not there? Will experience a lot of force in a short interval of time. That hurts us. Okay. If springs are there, when we sit on the seat, what happens? The spring gets compressed and it gets expanded later after the wheel is out of the pit. So during this time, what happens? Whatever force is supposed to act in a short interval of time, that force acts over a large interval of time and you don't get hurt. So that's the reason why we fix these shock absorbers to the vehicles. Okay, so these are few applications. Okay, let us try this problem. Find the impulse due to the force F bar is equal to 2I cap plus 4T J cap. So here force is not a constant. It's not a constant. It's a variable force. It's a time dependent force, right? If this force acts from T1 equal to 0 seconds to T2 equal to 0.3 seconds. Okay, so let us try to find out impulse. We all know that if we are dealing with a variable force, the impulse can be expressed as integral T1 to T2 F bar dt. That's how impulse is expressed if you are dealing with variable force. So here T1 is given as 0, T2 is given as 0.3, F bar is given as 2I cap plus 4T J cap into dt. So let us multiply this integral into the bracket, and what we'll have, integral 0 to 0.3 to I cap dt, or it would be more appropriate if you write it like this, integral 2 into dt into I cap plus integral 0 to 0.3 4t dt j cap. So that's how it can be written. So integral 2 dt is what? 2t. 2 is just a number, you can bring it outside. Integral dt is what? T. So what you will have? 2t. Okay, I'll write t 2 outside and I'll apply the limits 0 to 0.3 into I cap plus here 4 is just a number, you can bring it out of the integration. Integral t dt is what? T square by 2. So 4 into t square by 2 and apply the limits 0 to 0.3 into j cap. Okay, so let us make substitution. J bar is equal to, if you replace t with 0.3, you will have 0.3, 0.3 into 2, 0.6 minus 0, minus 0, it's a 0, 2 into 0 again 0, so no need to substitute that, into I cap. So 0.6 I cap plus 4 into, you can bring this 2 outside. When you bring this 2 outside, 4 by 2 will be 2. So you can write 2 here directly and replace this t with 0.3. Then what you will have? 0.3 square minus, you will have this lower limit into j cap. So 0.6 I cap plus 0.3 whole square, it's a 0.09. 0.09 into 2, it's a 0.18. 0.18 into j cap. So that's how the impulse can be obtained. Impulse, it is equal to finally 0.6 I cap plus 0.18 j cap. Okay, so let us try one more question. Now let us try to solve this question. A body of mass 2 kg has an initial speed 5 meter per second. A force acts, what is the initial speed? Initial speed is given as 5 meter per second. A force acts on it for some time in the direction of motion. So in the direction of motion, some force has acted for some time. The force time graph is shown in the figure like this. So find the final speed of the body. So how to handle this question? He is asking about final speed. Initial speed is given, mass of the body is given. Okay. So here the only way is, to identify the importance of this graph first. First thing to do is you have to identify the importance of this graph. We all know that FT graph, if it is given to you, area under the FT graph gives us impulse. Impulse, or it gives us change in momentum, because impulse is nothing but change in momentum, isn't it? Change in momentum is nothing but impulse, isn't it? So here, if you can manage to find out the area under this graph, that area gives us change in momentum. Change in momentum. And with the help of that change in momentum value, we can find out final speed. You know why? Change in momentum, impulse is equal to what? Change in momentum. Change in momentum can be expressed as mv minus mu, final momentum minus initial momentum, or m of v minus u. This is nothing but here area under the graph. So what we have to do is very clear. So we have to find out area under the graph and just equate it to m into v minus u, and you will be able to find out final velocity, because initial velocity is given, mass is given. So area under the graph you can find out from here, isn't it? So let us find out the area under the graph. Area under the graph is equal to, here there are few regular shapes here. This OAH is a right angle triangle. For right angle triangle, what is the area? Half into base. Base is 2. Height. What is the height here? 4. Isn't it? Plus. So we have calculated this area. This is equal to half into 2 into 4. And what about this area? ABGH. Length into breadth. This is a rectangle, right? So length into breadth. What is the length here? Length is equal to 4. Length is equal to 4. Breadth, 4 minus 2 is the breadth, 2. So 4 into 2 is the area. This one. What about this entire area? This entire area, this one. This small triangle's area we'll find out later. Let us first find out this entire area. From here to here, the length is how much? 6.5 minus 4, 2.5. And from here to here, it's 2.5. This is also 2.5 and this is also 2.5. So it's a square. G, E, D and up to here. This is a square. 2.5 into 2.5 is the area. Plus 2.5 into 2.5. Plus this small triangle's area. If this is also calculated, you will get the total area under the graph. Half into base. Base is equal to 4.5 minus 4. It's 0.5 into height. From here to here. What is the height? Equal to this much. Isn't it? 4 minus 2.5. It's 1.5. Right. So let me tell you again. This half into 2 into 4 is what? Area corresponding to this triangle. This 4 into 2 is what? Area corresponding to this rectangle. This 2.5 into 2.5 is area corresponding to this square. Okay. And half into 0.5 into 1.5 is what? Area corresponding to this small triangle. So the total area under the graph has been calculated. So let me simplify this. 2 gets cancelled. 4 plus 4 2s are 8 plus 2.5 into 2.5, 6.25 plus here what you will have? 5 into 15, 50, 75, 0.75 by 2, 0.75 by 2. This can be written as 0.23 27 and 25 0.375. So directly I will write in place of this, I will write 0.375. So let us add all these things. What you will have? 4 plus 8, 12. 12 plus this one, 6.25, 0.375. You will have 5, 12, 6, 6.625 plus 12. So you will have 18.625. 18.625. That's the area. That is the area. Okay. So what this area gives us? This area is equal to change in momentum. This area is equal to change in momentum. So let us equate this 18.625 to change in momentum. Therefore, m into p minus u is equal to 18.625. M is already known to us. How much is m? 2 k's. Initial velocity is also known to us. 5 meters per second. Therefore, final velocity from this equation, how it can be written from this equation? Final velocity v is equal to 18.625 by mass. Mass is how much? 2 k's. This minus u, if it is taken to RHS side, you will have plus u. Plus u is how much? 5 meters per second. So let us simplify this. What you will have? 9, 3, 1, 2. So 9.312 plus 5, it's equal to 14.312 meter per second. So that's the final velocity. So that's how you can find out the final velocity corresponding to this motion. Okay. So with this, I will close the session. Okay. Thank you, students. In the next session, we'll continue with the conservation of linear momentum.